Thank you so much, Stefan. Yes, indeed. We'll allow Dorsa to get set up. I'm delighted to introduce our next speaker who can get ready to share some slides. We're going to now have some more interesting human-robot interaction discussion, which is fantastic, right? Clearly part of the POGO efforts, Power On and Go. So as I said, it's my great pleasure to introduce Professor Dorsa Sadigh from Stanford, where she is an assistant professor of computer science and electrical engineering. Dorsa's interests really lie at the intersection of robotics, learning, and control theory. So three really, really rich areas, bringing them all together. And she's actually very interested in developing safe and efficient algorithms that are reliable and are focused specifically on human-robot interaction, right? Which is exactly what, if we're going to interact with people, we better be able to do it safely and reliably, especially in this Power On and Go fashion. Dorsa received her doctoral degree in electrical engineering and computer science, or EECS, from UC Berkeley in 2017, and also her bachelor's degree from Berkeley in EECS as well in 2012. And she's actually the recipient of numerous awards, including an NSF Career, fantastic, Google Faculty Research Award, and an Amazon Faculty Research Award. So we're delighted to have her here to speak to us. So with that, I will turn the virtual microphone over to Professor Sadigh to tell us more. Thank you.
All right, thank you so much. Thanks for inviting me and the kind introduction. So I'm really excited to be here. And today what I'd like to do is I'd like to take a different view on POGO robots and think a little bit about humans. And the reason I thought it is important to think about it is as I was reading the workshop introduction, like it came to me like thinking about like how we should go about modeling humans, how we should go about treating humans, specifically when we think about POGO robots. And what are some of the challenges and what are some of the opportunities that arise when we actually like treat humans as part of the loop and accept them with open arms. So that is my plan for the today's talk. And just to give you a background, so the way, when I started in the field of robotics, I was actually working on autonomous driving. So the thing that I was supposed to work on during my PhD was thinking about giving guarantees for autonomous cars. This was back in the day when autonomous car companies were still saying we are going to have autonomous cars by 2020. That was still like a feasible thing. But since then, like over the past decade, like we have seen a lot of advances in the field of autonomous driving. Like before, they were just driving on highways sometimes with some humans in the loop. But now we actually have them driving autonomously in cities, interacting with people. So lots of advances in this field. And I think part of it, like a large part of it, is due to having really good perception and control and learning algorithms. But I do think a large part of it is also due to understanding how we should go about treating humans when these humans are interacting with these systems. So back in the day, what I really wanted to do was to prove that these cars are safe. That was my goal of my PhD thesis. And the way I treated that problem was from a control theory and formal methods perspective. So the goal was, let's come down and sit and write, what is the objective that this robot needs to satisfy? What is my environment model? If I can write that formally through a specification, then what I can do is I can go and directly synthesize a controller that is going to be definitely correct and satisfy the specification. Can I come up with this provably correct controller? That was the goal. And then, of course, that's really difficult, and of course, it's hard to find such a controller, but we did attempt doing so, and we did have some nice results around it. For example, one common approach to go about this problem is to write down the specification using temporal logic, maybe. We could use ideas from automata theory, so we could generate a non-deterministic Buki automata, determinize it, generate a game between your autonomous system, which is your robot car or autonomous car, with the environment and everything that's happening in the environment, and then try to solve that game and come up with a provably correct strategy. At the end of this whole W exponential time algorithm, I will end up having a strategy that has guarantees. And that was kind of interesting, but the thing that was bugging me was there were a lot of assumptions here. To give any of these proofs, there were a ton of assumptions put in place. And we were pushing those assumptions under the rug, of course. But one of the assumptions that was bugging me a lot was the type of human models we were assuming here. And at the time, I didn't know anything about HRI. I didn't really know anything about how to go and model humans. I was ignoring humans like a lot of other people. They're like, okay, I'm just going to build my good autonomous system. Someone else will worry about humans. That's not my problem. And the way we went about modeling humans, we had to put something in there. The way we went about modeling humans was we talked to some car companies and they were saying, well, if your car is driving 60 miles per hour, it's probably going to drive 60 miles per hour for like the next whatever number of seconds. So just assume that it's keeping constant velocity. Like assume that model, everything will be great. So we put that model, and then under that model, we had a set of guarantees, which were great because now our car was driving so great right next to human-driven cars. And that was just not very satisfying. And at some point, I took the other extreme saying, well, I can't really assume that about this human-driven car. Maybe I should assume that the human-driven car is adversarial. And if I assume that the human-driven car is adversarial and is trying to like get me, then I don't really have any guarantees. Finding this controller is really hard, but I can do some sort of analysis. And that was also not very satisfying. So I had like these two ends of the spectrum and not knowing how humans are actually acting around me and being really frustrated by that. And this wasn't just me. Actually, like a lot of autonomous car companies who were not worrying about this problem were actually starting to worry about it. This kind of started in like 2015, where Google started putting out their cars on the road, and in only like a few months, they had 11 accidents. All of these accidents, the Google car was being rear-ended, so of course it wasn't Google's problem. But like, why is this car being rear-ended 11 times in a span of a few months? And one could argue that the reason is it wasn't very interactive. It wasn't really thinking about the interaction with human-driven cars on the road and how these humans are behaving around it, and the fact that they're not like playing like a robot. These humans are not behaving by the book, and one needs to actually think about that and worry about that. This is a video from like even like a few years back, so it's not like all the way to 2015. This is still a problem. So here is a video of a Waymo car that is trying to be interactive. It is signaling, so I'll give that to it. It is signaling and trying to be interactive, but its motion is not giving you anything, and it's not trying to be interactive through its motion. So because of that, it's in the exit row, so it has to like exit and come back around and try to change lanes, because through its actions, you don't really like see any interaction with humans or modeling how humans are responding. So I think this idea of ignoring humans is not going to get us anywhere. So because of that, I think we got to accept them. And if you're accepting and embracing them, might as well accept them with open arms. So in the driving work, the way we started thinking about interaction was we started thinking about it a little bit more carefully. We thought about having an autonomous car, the orange car, interacting with a human-driven car. And well, we thought about this human-driven car having a human inside it, and the fact that that human has a model of the world and also tries to optimize for reaching for its destination and do the right things. So based on this model of the human, we started being a little bit more careful about how we think about interaction. And we modeled this interaction using a game theoretic framework, thinking about it as an under-actuated dynamical system, where we say my autonomous car, my orange car, is going to follow a policy that's a maximizer of a reward function. Very good question to ask is, well, what is that reward function? Reward design in general is a very difficult problem. I'll come back to that point later in the talk. And then the second point is this reward function should depend on the actions of the human. It shouldn't treat the human as a moving obstacle. And the question is, well, how are we now going to go and model this human? Like, who is going to model the human? And the way we went about it was we modeled the human car's policy as a policy that's a maximizer of the human's reward function. So we said, well, the human probably has a reward function. Let's just take the maximum of that, and that gives us the policy of the human, which is far from accurate. I agree with that. But it's an approximation, and I will come back to this point of, is this model even right, a little bit later in the talk. And this was actually an RSS work in 2016. And using this interaction, what ended up happening was we ended up seeing really interesting behaviors. What we ended up seeing was seeing a car trying to change lanes in a much more interactive way, trying to kind of cut in front of someone and nudge in front of someone and change lanes through that. This is very human-like, right? Like when humans change lanes, they don't wait for every single car to pass. Like they start nudging in, then they think about interactions a little bit more carefully and they're more assertive. So it was exciting that now that we're accepting that humans exist and now that we're modeling them, we are seeing these more interesting, useful behaviors for the robot. Like for the robot's sake, like we are seeing like really useful behaviors now that we are actually paying attention to the human. And that was really exciting, and that made me start thinking about, well, what can we do now that we have to think about humans? So in this talk, what I'd like to do is, I would like to talk about a set of opportunities that we get when we actually accept humans with open arms. And specifically, I want to talk about the data problem here. So in general, for robotics and robot learning, having data and having useful interactive data is really difficult. And the good thing about humans is that they tend to leak information all over the place. So because humans leak information, I think we have an opportunity to learn from humans, even just for the sake of robotics, not for the sake of HRI, just to get better robots. And then for the second, kind of like towards the end of the talk, what I'd like to do is I'd like to talk a little bit about some of the challenges that humans bring in. So that's the plan for today. All right, so let's just get into it. So why do I think this is an important problem for just robotics in general? So this is a, let me just motivate this a little bit more. This is a project that we submitted to RSS last year. This was a joint project with Chelsea's group. And what we were trying to do was we were trying to do a robot learning project where we have an initial image and we have a goal image. And all we want to do is we want to get the robot to push this goal, push this object and push it towards the goal. And the way we were doing it was interesting. So the way we were doing it was by learning an unsupervised latent space that actually measures progress towards this goal. So we wanted to really figure out that latent space. And through this process, like this is, again, generic robot learning, like has nothing to do with HRI. But throughout this process, what we needed to do was we needed to collect lots of data. And no one talks about this usually, but lots of data. And every time that this robot would move any of these objects around, we had an undergrad, Gleb, who would reset the environment. So Gleb was like sitting there all night and basically like resetting this environment for the robot. Of course, there are smarter ways of handling this. I know a lot of people who work on robot learning have a second robot that resets the environment for the first robot. We were naive in handling this problem. But in general, data collection is really hard. And the thing is, we have this human in the loop. And because we have this human in the loop, maybe we can be smarter about how we query our humans and how we are collecting data from our humans. And we should be a little bit more careful about informativeness of that data and diversity of that data instead of collecting random trajectories. So what I'd like to talk about is the fact that we need to have a data-efficient approach that can actually learn from interactions with humans in order to learn maybe a reward function for a robot that can go ahead and do interesting things in the world. So one setup for that, which is a very common setup, is I can have a human expert come in and demonstrate on a robot how to do a thing, like pick up an object. And based on those demonstrations, based on those expert demonstrations, this robot can go ahead and build some sort of representation of what is this reward function that the human really wants me to optimize? Like, what would that look like? Okay, so that is imitation learning or inverse reinforcement learning in this case, if you're learning a reward function. And one can go ahead and do that using demonstrations. But the thing is, expert demonstrations in general, they're noisy and they're expensive. Like if I want to collect expert demonstrations, I would need to ask Gleb again to come in and provide that expert demonstration here. And in general, controlling robots with high degrees of freedom is known to be really difficult, as we see in the assistive domain already. So the idea that we've been exploring around is that demonstrations are only one form of data. In general, we have a lot of other sources of data from humans that we can leverage. There are different sources of data that humans provide to us. There are demonstrations, there are comparisons, pairwise comparisons between trajectories or rankings. There, they don't need to provide any demonstrations. They can just sit there and rank things. They can provide language instructions, which is really useful because it gives us kind of like where to pay attention to, and it's an abstract form that tells us what features actually matter. You can look at physical feedback where the human actually physically moves the arm, and from that physical feedback, you can learn a lot of information. So in general, in my lab, we have been thinking about these different sources of data and how we can combine them and integrate them in an intelligent way so we can quickly learn robot reward functions. And today, I don't want to talk about all of these. The only thing I want to briefly talk about is how we go about combining demonstrations and comparisons. I'm now going to talk about some of the language and physical feedback work. But I'm going to mainly talk about comparisons and its integration with demonstrations. All right. So what do I mean by comparisons? What I mean by comparisons is I can basically show two different trajectories to this human, and I can ask the human, well, which one do you prefer? Do you like A or B? And the human's response to this single binary question is going to give me some information about the underlying reward function. And currently at the moment, I'm assuming this underlying reward function is a linear combination of a set of hand-coded features. So every question I ask in this space is going to generate a separating hyperplane. The human's response tells me which side of the hyperplane is preferred. And based on that, I'm going to update my hypothesis space about the reward function. So the question that's, I think, interesting here is, could we ask for the most informative, diverse sequence of queries that actually get to the core of this really quickly? And the way we formulate that is an active learning problem, where we try to actively synthesize these interesting scenarios and then query the person to quickly learn what that reward function looks like. And what that looks like is, it looks like a single optimization that we run at every time step. So at every time step, I'm saying, generate the scenarios, generate the fees that maximize the minimum volume that would be removed from the hypothesis space based on the human's response. Okay? So that allows me to generate these informative queries, subject to the fact that the queries are actually feasible and that they can run on a robot. And also, we have another assumption that all humans are going to be noisy. I'm not going to completely trust what the human tells me because they're noisy, and I should take that into account. But by doing so, I can generate these interesting queries, and based on these binary questions, I can learn some stuff. It's actually quite useful to learn from just binary questions. So after 0 queries, this car has no idea what to do because it hasn't asked anything in the simulated environment. After 30 queries, 30 binary questions, the car learns how to keep heading. And then after 70 questions, the car learns how to drive in this like simulated environment, like do collision avoidance and keep heading and things of those forms. And again, this is 70 simple binary questions, nothing fancier than that. All right, so that was preferences. Preferences, they're kind of useful because they're very easy to get, and they're very accurate. Like if I ask a person, do you want to hit a car or do you not want to hit a car? Like I can kind of trust that answer. So that gives me a lot of information. But the problem with preferences is that they only give us one bit of information. They're not much more informative than that. It's like saying if A is greater than B or B is greater than A. On the other hand, there's a ton of work around learning from demonstrations and learning from experts. And that is also interesting because demonstrations can be really rich and informative. You can get the style and timing of the trajectories and all of that. But the problem with demonstrations is that they tend to be noisy and a lot of times inaccurate. I haven't shown the videos of our demonstration collections, but they tend to be really kind of like inaccurate and hard to get it, like do the right thing. Because again, controlling these robots with high degrees of freedom can be really hard. So what we've been exploring is what is the most what is the most optimal way of combining demonstrations and preferences? If I have access to these different sources of data, what would be the optimal way of combining them? And it actually turns out we've proved that the optimal way of combining preferences and demonstrations is to warm start with demonstrations. So we warm start our algorithm with a set of demonstrations. That allows us to have a better estimate of how this reward function looks like, kind of like get a form of it, get a shape of what the reward function looks like. And then afterwards, once we warm started this with demonstrations, we can fine tune it with generating new queries and asking for preferences. So I can basically generate 2 new trajectories, T1 and T2, and maybe I have my original demonstration, and I can ask a user, well, can you rank these? Or can you do a pairwise comparison between them? And I can do this loop until I have a better and better estimate of the reward function. Okay? So let me show you how this works in practice. So we looked at a setting where we collected demonstrations on a robot, and we tried to get the robot basically avoid the obstacle, which is the box here, and move it from one location to another location. For example, getting to this black pad. And then in test time, we changed the scenario a little bit. Like we have the box on the other side, and the robot is supposed to reach the top of the Pringles box. So what happens here is that the robot, in the case that it's just learning from demonstrations, it starts off okay, but because its demonstrations are kind of noisy and don't really reach the goal, what ends up happening is the robot ends up in a weird configuration where it thinks obstacle avoidance is so bad that it never reaches the top of the Pringles box. But when we are actually warm starting with demonstrations and fine-tuning this reward with a few preferences, we are able to reach the top of the Pringles box using this algorithm. And again, this is with very limited data. This is only like with a few demonstrations and a few questions. And we are able to learn this general reward function that applies in new setting and then gets the robot to reasonable behaviors here, which is kind of exciting. So just to summarize, the key idea here that I've been talking about is the fact that we got to integrate demonstrations and comparisons and in general different sources of data that we can get from humans to learn reward functions, and think of humans as an opportunity that allows us to be much more data efficient in our data collection to build better robots and to learn reward functions. And so far, everything I've said is about this linear reward function. And I didn't say anything about fancier than that, right? Like this linear reward function needs to have a set of hand-coded features and a set of weights. And in general, writing out those features and coming up with those weights is really difficult. So I think this is not, I don't need to convince you guys that designing features can be really challenging. If you look at papers that use linear reward functions, there are usually statements in the experiment section saying, well, we picked a feature that was an exponential distance of some c times some distance, and that c was equal to 3. And where does that 3 comes from? Magic, reward design, hyperparameter tuning, all of those could be part of it. Sometimes you have even like much more complicated features, like using quadratic distance with 2 other parameters, 7 and 3, which again, like God knows where they're coming from. In general, like this is hard, right? Like writing out features is hard, and it's an old problem. Like this is not a new problem. Feature generation is an old problem, and one solution that people have come up to with is using deep learning, so then you avoid generating features. But the thing is here, when you're collecting data from humans, like we can't really train like a full neural network just based on data that's collected from humans. That's not going to really scale. So we got to be a little bit smarter and be somewhere in between, where we actually use features that are reasonable to design, but then we are able to be more expressive in terms of behaviors that we can see on the robot. So in a new work, this is actually an RSS work here. We're looking at a different task. This is a fun task. It is playing a version of mini golf, like basically getting the ball in any of those like small bowls there, like whatever the human prefers, based on this idea of preference-based learning. And we are choosing the simplest features that one can think of. So we're not really like trying that hard to come up with better features. And if you pick a linear reward function, optimizing that linear reward function always thinks the optimal thing is to go to these 4 different corners. Like if you optimize that linear reward function, you'll always end up in these corners and you wouldn't be able to like go for any of the other targets. So ideally we would want to have a better way of having like a better coverage, and ideally we would want to have a nonlinear function over these features and to have a better coverage. And as I mentioned already, like if you were to use a neural network, this human teacher that's responding to binary questions is not going to be very happy. But instead we just use a Gaussian process where this Gaussian process is going to be much more efficient and uses the same simple features in order to learn how to do this task. So I just want to show you quickly the learned policies of that and how that looks like. So if you were to use the linear reward, this is the learned policies. It ends up like going to the corners. But if you use the GP reward, you would be able to actually shoot for any of the other targets. And there's quite a bit of math that goes into this. Basically, the posterior ends up not being a GP, so we have to make a set of Laplace approximations to make that work. But if you're interested in the details of that, this is a paper that will be presented on Wednesday, and Erdem and Nicola are leading this project. All right, so that kind of summarizes the key points I wanted to mention as this part of the talk, like integrating demonstrations and comparisons and basically going beyond linear reward functions and taking this opportunity that there's a human here, I can learn from this human, that could be really useful. But now kind of for the last few minutes, what I would like to do is I'd like to step back and think about what are some of the challenges that these humans are creating. Sure, they're great, they give me data, I can be smart about it, and I can learn useful things for robots, but they also introduce quite a bit of challenges. Specifically, how should I go about modeling them and coming up with computational models of them when we are in various scenarios? So if you remember my formulation early on, well, I was modeling my humans as agents who are optimizing or approximately optimizing some sort of reward function. So the idea was there's this optimal action based on this reward function, and I would assume that my humans are rational and they're going to take that optimal action. Okay? So they're maximizing that reward function. And in general, I think we all agree humans are not always deterministic, doing the rational thing. So the field over the past few years has been coming up with better ways of modeling humans. Specifically, a very commonly used model is this noisily rational model, which says, well, humans are not deterministic, they're probabilistic, and probability of actions of humans is proportional to exponential of some theta parameter times some reward function. And this theta parameter is just a temperature parameter. It's usually known as the rationality coefficient. And if you put that equal to infinity, then you get your optimal actions. And if you put that equal to 0, then you get random actions. You assume your humans are random. And for anything in between, you would end up getting kind of like a nice curve here, trying to figure out the model of the human and being probabilistic about it. The problem with the noisily rational model of the human is that it still assumes the most likely action of the human is the optimal action. And that's not always the case. So the thing is, when we are in risky scenarios, when we are in near accident scenarios, it's not true that the optimal action is the most likely thing. There are a lot of cases where there is a suboptimal action, which is actually the most likely thing that people end up doing. So what we would like to do is we would like to be able to have a model that can capture what is shown in the orange plot here. And you might say, well, that's a reward design problem, right? Like just pick a reward function. So then for that reward function, your optimal action will be the orange line. But reward design is really hard. I don't want to spend all my life like coming up with like the right features and the right scalars, right? Like that is in general really hard. I want to come up with the most natural reward function one can come up with, but still be able to handle risky scenarios where the most likely action is not the optimal. And to be more systematic about this, the way we approach this problem is by using ideas from prospect theory. So specifically, we still use the same model. We say probability of actions of humans is proportional to exponential of some theta parameter times some reward function. But then the reward function is not the same old reward function. We actually make a set of nonlinear transformations on the reward function to capture risk. And since I don't have too much time, I'm going to just skip through this really quickly. Basically, we take the reward and we make a nonlinear transformation, and this nonlinear transformation is the same idea that people have a hard time differentiating high reward things, like they have a hard time differentiating between $1 million and $1 million and 10K versus differentiating between $1 and 10K, right? Like people have a hard time differentiating between those large values. So that nonlinear transformation with a set of hyperparameters is able to capture that. And similarly, we incorporate another human bias, which is in the probability, and then we make nonlinear transformation on the probability, basically overweighing low probability events and underweighing high probability events. This is again the same phenomena that when people go and buy insurance or buy lottery tickets, because they tend to overweigh low probability events. So basically adding these nonlinear transformations on the reward function is kind of like a more systematic way of capturing risk on top of our usual reward. And just to quickly show you how this would look like in practice, I'm showing just one simple example where we have a robot and a human coordinating with each other on a simple block stacking task. Okay, so in this setting, I have a human and robot putting blocks on top of each other and building towers. And they have two options. They can either go and build an efficient but unstable tower. This is kind of like the Tower of Pisa. So basically, if the tower stays upright, they get a lot of points. They get 105 points. But the thing is, the tower only stays upright like 20% of the times. So it's very efficient, but it can be unstable. On the other hand, the human and robot could coordinate together to build an inefficient but stable tower, putting these cups on top of each other in a decreasing order of size to make sure that it never falls. But then if you're building that tower, because it never falls, you're only going to get like 20 points. You didn't do anything that big of a deal. So if you compare these two scenarios, it turns out that taking risks and being efficient about it and building that unstable tower, that piece of tower, is going to be actually the thing that is the optimal thing to do. So an optimal human should take risks here. But when we run this study with humans, it turns out that our humans are overly concerned about the tower falling, because this is exactly a risky scenario. And then they're really concerned about this tower falling, and most of the times they're actually not taking risks. And if you have a robot that models the human as a noisily rational human, then that robot wouldn't realize that, and it would go for the same cup that the human goes for, and then the robot needs to replan and go back around and pick up a different cup. You see this in action here? Roberto goes for the orange cup, the robot also goes for the orange cup, and it comes out empty-handed, and it needs to replan. But instead, if you use this idea of risk-aware modeling and capturing the fact that humans are going to be overly concerned here, then the robot correctly predicts where the human is going to do, and based on that, plans accordingly and basically collaborates and coordinates with the human much better and much faster. Okay, so just to summarize, the key idea for the second part of the talk is modeling humans can be difficult. They're not always following the same policy. And then there are a lot of times they tend to be suboptimal when we are in risky scenarios. But there are ways of handling that. And one way to go about it is using ideas from prospect theory to capture these suboptimalities when it comes to interactions with humans. And just one last thought around this idea of thinking about humans and being careful about humans is something that we're more recently thinking about a little bit more carefully, and that's the idea of adaptations. Like everything I've said so far in modeling humans was assuming there was a fixed reward function, a fixed policy, and then we will learn it and we'll be done. And the thing is, in general, humans tend to adapt. I've been driving and biking around these cruise cars in San Francisco these days, and now when I see them, I usually go around them because I think they're probably stuck, because I've had a few interactions with them when they were stuck. So my behaviors has actually changed based on those few interactions. And that's kind of interesting, like thinking about how humans adapt and thinking about the fact that this cruise car needs to actually realize that I've adapted and take that into account, again, for its own sake, not for the sake of human-robot interaction, for its own sake of safe driving in this setting. It should realize that my behavior has adapted. So with that, I'd like to thank you guys, and I can take any questions.
Just clap. Perfect. All right. That was fantastic. Thank you. I always thought an exponential was 7 and 3 was always the way to go. Those are the numbers I always pick. 3 and 7. Those are the best numbers. I didn't know there were other choices actually. No, that was great. That was great. So we have time for one question, and I'm going to take one that was posted in the chat, and I'm going to kind of paraphrase it and add my own little spin to it. That is a question about outliers in the context probably of the driving. Let's just take driving as an example. If you're modeling the risk scenario, let's say, what do you do about the jerk? Like the person driving who is just, or the person that is in an adversarial sense, out to sabotage your Waymo or cruise car, in the sense that, and people do this on the freeway, the person, or the robot has to get over into your lane, and you just decide as this jerk driver, no, I'm just going to keep driving, and this thing, the car is going to try and get over. I'm not letting it in. The Waymo vehicle would have to hit me. I need the insurance money. Is that incorporated, or do you just, in that case, does the car at some point does the car say, normally I like people that are kind of rational within some 3 sigma maybe, but this person is just like 9 sigma jerk. I give up. Is that, or do you decide as a vehicle to just be like, I'm gonna do what a human driver might do, which is just muscle in regardless and say, take the chance that maybe these people, this person driving values their vehicle enough that they don't want to get hit.
I think that's a very good question. That's a very good question. And I don't think there is like a clear answer necessarily for it. But I think in general, like keeping track of an estimate of the drivers around us can give us a lot of information. In general, like autonomous cars could be really good at that, and keeping track of an estimate of, oh, this guy's probably a jerk. I saw it, like it interacting with this other car, like cutting in front of it. So maybe I should be more careful about it. That's like how we as humans do, like detecting more jerks. I think in general, we could do something of that form. And probably autonomous cars are going to be on the safer side of things, and they would like at some point they would be like, okay, I'm gonna let you go. But that's in general a good question. Should the autonomous cars always like go on the more conservative side? And if they do, humans are going to realize that and always cut in front of them. So is that really what we want to do? Yeah. So I think safety is a big problem that we haven't really solved it yet, and we haven't really figured out how we should go about safety of these vehicles. Are we going to let them not be like the safest car, and are we going to be happy with that? I think that's also a perfect, like not a perfect solution, but that's a perfectly fine thing that could happen. Like we realize, hey, these autonomous cars are also sometimes jerks, and maybe that is fine.
Absolutely, yeah. Well, it could almost be a no-win. You know, it's a no-win game in some sense, right? If you always, as a robot, if you always give way, then of course the people are eventually going to probably drive all over you in some sense, right? And on the other hand, right, if you're, you know, if you, I don't know if who pays the insurance for the Google, but at some point maybe the Google cars just need to scrape just like a light bumper touch or something, just to say, I don't know. Anyway, okay, that's fantastic actually. We have maybe one quick time for one more, just last quick question, which was also brought up in the chat partially. That was about basically data efficiency of the processes that you spoke about. So if you had a more complex task, I mean, those tasks are already quite complex, like stacking and the Pringles can grabbing, for example. But if you had something that had multiple steps involved, like beyond those steps, like a long horizon task, do you have a feeling for just how much data some of those long, I mean, I don't have a canonical example, but a longer horizon task might require, like human preference or human demonstrations, etc.?
That's a very good question. Yeah. So we looked at like more specific, like goal-oriented type of things as opposed to a long horizon task for a lot of these things. But if you consider more complex tasks generally, like in the space of the linear report, that would introduce just a lot more features, and that could become unscalable at some point because the number of dimensions you need to search in expands. But in the follow-up work, in the RSS work this time around, like we have this Gaussian process kind of approach, this active learning over Gaussian process type of approach that can handle some of those more complex settings, like getting the exact like target location for the mini golf task. So I think that could address some of the issues. But in general, for some of these more longer horizon tasks, we are taking a slightly different approach. Actually, we're taking an approach where we are getting language instructions, and then based on the language instructions, we can kind of get the steps right, and then combining linguistic data with demonstrations, and how do we go about that combination is something we're thinking about. Gotcha.
Oh, fantastic. Very, very interesting. Okay, well, let's thank Professor Sadigh one more time. Just give you our semi-virtual clap. And okay, we now have